Okay, good. This is your next session. Warm welcome. This session is about graph-based network topology analysis for large telecom operators. Let me introduce Franziska. Franziska Schmitz is our data scientist, and me, Andreas Lattor, I'm the network scientist. We both work for Sopra Steria. Sopra Steria is one out of 10 IT strategy consulting company in Europe. So we organized in verticals or specialized in verticals like banking, insurance. So, and we both work in the telco domain. So we are 2 out of 2,500 other experts in Europe. Yeah, and we are here now. Thanks for Neo4j for this invite. Happy to speak about our use case here, which is about we have copied a complete mobile operator's network topology into Neo4j. So complete copied, this is updated every day. So, and we build a kind of digital twin. So what is the benefit out of doing this? If you ever tried to change a tire wheel while the car is driving, so complicated, yeah? But our customers, operators must do this. So they have to change their network while the network is running. Customers do not accept frequent outages, and they have to change the network. About 1,000 changes per day, alone in transport domain, 1,000 changes per day. And this is all driven by a huge CapEx investment into the network evolution, 5G, fiber rollout, and all this. So, and this is such a network is a very complex graph or network topology, consists of different layers. So, and most of the issues we have on the network are caused by a previous change. Let me further introduce into the subject. Knowing we are not all coming from the telco domain, coming more from software engineering. So in software engineering, it's like this. You have your UML diagrams, you have your Swagger definition. Out of this, you compile your code skeletons, client stub, server stub, all this, and this is then programmed and unit tested over, let's say, a well-defined CI/CD pipeline. You have your quality assurance. So everything is complete in sync. Your Swagger, your UML diagrams, everything is in sync. So imagine now, your Swagger or UML diagram would not be in sync, and you start your project. And this is exactly what's happening day by day in telco domain. So they have their network in an offline documentation system, which is representing the network, but is not completely in sync. So, and imagine now you start your network project, and this is not completely in sync. Out of such a network project, the relevant network configuration will be prepared and compiled, and later on applied to the network. So, and this is exactly the problem. If you activate a configuration which does not completely fit to the network, can cause an issue on the topology. So this was the idea to build the digital twin. We call it intelligent network analyzer. That means we extract the complete data out of a huge mobile operator day by day over all the details with status, config, performance, out of 30,000 routers, 50,000 switches, 80K radio station. So this is all extracted out. And then the most complex thing starts. You have to ingest this into your system regarding semantics and all this. So we did this, feed this complete into Neo4j. So you have the complete topology in. And once you have this, you have done this. So this is then very easy. The game starts. Then you can analyze the data. So analyzing the data, in our project, there was the demand. We should provide a front end, easy to use for network operators, for hundreds and thousands of users, and without any training before. Should be watch a video and then kick off and start. So therefore we decided not to buy an off-the-shelf product. So we developed a specific product out of this. We have a look later on. Along with this, we have provided a few analysis, predefined analysis. We also have a look later on this. So for our use case, it was the perfect fit. And we're great that we have got, let's say, so powerful frameworks here. And we are using Neo4j. It's the core of our solution. And network, an operator's network, is a graph. So that helped us a lot here to start with the graph database. In this database, we have config status and also dynamic data, performance data we are loading in. So in addition, we have some nice frameworks, which is a Python framework, networkx. We are using intensively also the GDS, Graph Data Science Library. And on top, we built this custom user interface, with, let's say, this simplified user interface, which represents the graph. So it's like this. It's a very simple front end. And one major design decision was we present a graph directly to end users, to network engineers, network operators, and they do not understand graphs. So they understand Visio drawings, network diagrams. So we need a front end which is similar to Visio, have a flexibility and show them the real graph. So that we have, what you see here is a graph, and the nodes and the node icons are set based on the node label and also some other properties representing the status and so on. So it gives us the flexibility and also the edges, the size, color, and we have a specific visualization implemented here specific for telco, showing the utilization of an edge, of a link. But doing the upload of the network and updating the documentation in our twin is not enough. And you need to, let's say, build the network functionality in the twin. So the network functionality means you have packets, routing will be routed through a network. So you need also the logics to do that. So that means we have to build in router functionality, switch functionality, not the complete, but let's say the major functionality of forwarding packets. And if you look into the details here, you will find some parallels. So routing protocols act like graphs. We have weighted shortest path. It's OSPF routing protocol, very similar. We have spanning tree and that. So, and peerings, information, IP addresses, and this we stitched all together to build up this really, let's say, a live digital twin, which enables us to have really different analysis, root cause analysis. We can do dry runs, impact analysis, and all this. This example here is simple, what I showed before. A real operator network, it's very huge. So we have about, typically an operator in Germany, one mobile operator, has about 30,000 routers, all connected. One router has an average 100 ports. This is all stitched together. So, and you have, in addition, you have status on links. You have different sub-networks, gateways. Sometimes you have the weights in sub-networks. They are equal, load sharing. So, and this all, thanks to the graph database, was possible to build in our project in about 1.5 years. Okay, so now I will hand over to my colleague. Franziska will introduce us into more specific analysis we have implemented. Over to you.
Okay, thank you. Can everyone hear me? Okay, great. So what we have here is an example which is very similar to the problem I will be talking later. So I think everyone had this problem before sitting in a traffic jam or congestion. And if you use Google Maps, it will provide you some other ways so that it's not so highly utilized. So maybe you have to take another road and it's longer than this one, but even though you will arrive earlier because you don't stand in this congestion. And exactly the same is what INA does. So here we have a network, and these dark red lines indicates very highly utilized edges. And what INA does is that it provides other routing so that the edges won't be as utilized. And the same as in the traffic congestion is maybe some routers will take a longer path, but then the network is more balanced. So we have a problem where many options are for each router. So each one can take 5 different paths, because each of these blue routers, which are access routers, have to find one of the yellow ones, the aggregation router. And so you have many combinations. It's 800 billion. And if you assume you will it will take 1 millisecond for each configuration to test, you would need about 25 years. So this is not an option, obviously. So what we do is another thing. We use simulated annealing, which is a stochastic optimization way. And so we can find a very good solution with only testing 1,000 combinations. And so it will take about 1 minute. And this is what we get after this. So again, we can see these dark red lines, which are indicating very high utilization on the left-hand side. On the right-hand side, you can see how the network looks after the optimization. And now you can see there aren't any of these left edges. Of course, in some parts, the utilization gets higher, for example, this one. So, of course, if other paths are used, there will be some of these edges which have more utilization. But if you look at it, you can see that it's much more balanced than before. So, to put it in a nutshell, what is the great thing about INA? So first of all, you get this digital twin, and you can look how the topology looks right now. Secondly, you have an analysis which all network elements, switches, routers, antennas, and so on. And as I just explained, we have the optimization, which can help a lot to find better configurations. Okay, let's start with a demo of the tool.
Okay, then let me take over. Let's have a look. So that was PowerPoint, and let's have a look to an example. So the complete demo is running on the laptop here. We have the Neo4j locally installed, and also the front end and everything is on this. Is a little laptop. It's an i5, and we have 8 gig of RAM here. And what I present, it's synthetic data. It's not a real data, but it is very similar. So okay. 9. Yep. Okay. Here we are. Let's do it. Let's go on. So in general, so it's a graph front end. So you could connect to the database here. So I have some adjustments. So this is a normal front end. Let's extend this here. So we have different options to select. So we have for the analysis section, we can display the graph on the map, and also historical comparisons. So that will part of the demo. Let us kick off. So now, dann habe ich das Netzelement verloren. That's real life. So this is a good example here, so therefore I'm select this. Okay, so it's selected. So here we are. So this is a simple node. Here, a radius representing one radio station. And you can see the attributes on the node. Those attributes, as you can see in the Neo4j browser, so it's similar, the attributes. We have not presented all, the major set here, but it's representing the position of this node in the graph. So it's pre-analyzed, like the connection chain, how this node is connected to the aggregation network, how many hops do we have to reach the main border router. So very simple to use. So we have the menu that will be configured specific on the node and the use cases. And underneath, so if you do this, so in general a cipher query is executed underneath. And we have specific visualization, as I said, of the nodes, specific labels here. We have a radio station here, and color coding, which is representing, for instance, the link status direct. We have coloring here. Yeah, and from here you can, in general, navigate to the complete network. Everything is connected end to end. You can select either a node direct, or a specific node, BTS, router, or even you can add a connection, means an edge. So from there, clicking the right mouse here, going further, please show me the access network. So this is a cipher query showing the access network. Zoom a bit in. And this is here in general, so we have, it's a simple graph, but we have the edges and icon specific configured. For instance, you have directly capacity between two routers. And now it starts, we did further analysis in, for instance, we built up the routing here. So this is the routing path. This station will route the traffic over the 3 access router towards the aggregation router. So the same is done also for other combinations. So you have everywhere the routing is available. So and this is for, let's say, for the telco use case, this is very important because everything is completely reflecting the network. There is nothing with manual documentation in it. So as I said before, we also have traffic or performance data in it. And we have this is the access traffic coming directly from the radio station. And we have this for each of the, let's say, nodes, the entry nodes, the traffic. And we can aggregate now the traffic over the topology. We know how the traffic flows. We have the routing protocols. We have the edge traffic, and we can route it through the network and see how it is. And we can do it like here. We have a special visualization here. We use the water pipe. We call it water pipe visualization, representing the traffic between the edges. So now you could say, you can measure the traffic between the edges, between the nodes. So this is clear, we are doing this as well. But we use this measurement to compare the real, let's say, traffic against our calculation. So, and we validated this. So this is, if this matches together, our calculation is correct. So, and this is the entry level into simulation. So that means if you can do this, you can cut an edge. What happens then with the traffic flow? You can add an edge, increase capacity, whatever you like. Huh? You can modify this and recalculate the traffic. Okay, so one thing, let me check this here. Clear this here quick to show that it's so simple. You all know this, so this is a very simple cipher. There is one router and there is an edge called router to router to another router. Very simple cipher. So, and if you use, will not pollute your if you use the front end, here you can also copy the same cipher into our front end, run the query, and then the icons are attached. So the graph becomes readable here. So this is like a Visio diagram, and if you do it with the normal way of graphs, so it's not directly readable, yeah, here. Simple idea, adding an SVG as icon, but then the graph becomes readable. Okay, good. From here, I would like again hand over to Franziska, showing some more advanced analysis.
Okay, so the first example I want to show is the impact analysis. So we want to know which BTSs are impacted by this router. So let's see. Okay, so here we can see that there are antennas which are not connected directly to this router, but are also impacted. So why is that? Let me show the whole router cluster, then we can see what's going on. Okay, so as I told you before, each of these routers and antennas have to reach one of the yellow aggregation routers. And as you can see, that this antenna and this router couldn't reach any of the yellow ones if this one goes down. So that's a very powerful tool because it's helping you with the troubleshoot and the ticket system, and so it really saves a lot of time and money. What you can also see here is that it's very helpful to plan the network. So for instance, you see that that one is very dependent on that one, and you can see that there's a very, very simple way to make this more more secure. And that's, for example, if you would do an edge between these two, because then that one could reach this router over there as a backup, and it wouldn't be such a problem if that one would go down. Okay, the next thing I like to show you is our map. So you see that this is a very good overview of the network, and every network planner likes to have that view. But you can also see it in the map. So here you can see where these routers actually are located. So where we are, let's see. Okay, we are near to Nieburg-Weser. Never heard before of that. Okay, but also you can click on these routers and see every information which is important. So it's the same information as in the Explorer before. And also what is great about this is that you can see how your network elements are actually located with respect to each other, which isn't the case in the Explorer, because there you try to have a good overview instead. Okay, let's go back to the Explorer, and there's another thing. You can import and export your data. So why is that? Because maybe a planner wants to see which he wants to change the network, maybe insert some routers or edges or antennas and so, and then on the next day he wants to go on with it. But it wouldn't be there because the network had changed maybe overnight. But what he can do is he can export its topology. So if he comes back at the next day, he wants to see, he wants its old configuration to see, but it might have changed. So there's an import, and he can select the thing he has further exported. Okay, we had the 30th before, great. Yes, and here we go. Now it's exactly the same configuration as before, and the planner can go on. Okay, there's one last thing I would like to show you, and this is the history. The history tab is also here at the top. I have prepared an example before. Let me see which one is a good example. I will take that one. Oops. Okay. So, start to analyze is a BTS, and that's the name. There's a space. Okay, so here it is. Here are very much informations about it, and let's see how the path to the access router is. Okay, so here we can see what happened before. Okay, and now we want to see how the history works. So we do the exact thing as before. We select the same BTS. So we are just on the 30th, and on that day the path to the router access was the same as before. But what if we want to look at it and how it looked at the 25th? So here's a slider, and we can slide over there. So let's see what has changed. Okay, that looks completely different. And the reason for that is that this interface is down. And we have these green dots indicating that there has actually been a change. So obviously both changes are because this interface has go down. And here we can see that two things has changed about this antenna. So we can see here the base, router base interface. That one has changed. Okay. So that's it. And I can see we have a few minutes left for the Q&A.
Okay, good. Thanks, Franziska. Yeah, so we have a bit of time. So are there any questions? Yeah, yes, please.